What is gears? Gears are used to transmit power and rotating or reciprocating motion from one machine part to another. Yung gear ay yung rotating circular machine part in which evenly spaced teeth are cut. They may be classified according to the position of the shafts that they connect. Parallel shafts, for example, may be connected by spar gears, helical gears, or herringbone gears. Interesting shafts may be connected by bevel gears having either straight, skew, or spiral teeth. Non-parallel, non-intersecting shafts may be connected by helical gears, hypoid gears, or a worm and a worm gear. A spar gear meshed with a rock will convert rotary motion to reciprocating motion. As you can see in the picture, ay may parang mga ngipin na evenly cut. Yan yung gears.
Spar gears definition and formula. The friction wheel shown in figure 20.2, it transmits motion and power in one shaft to another, parallel shaft. However, friction wheels are subject to slipping and excessive pressure is required between the wheels to obtain necessary frictional force. Therefore, they are usually used in low power applications such as phonograph and turntable drives. If a friction wheels of a diameter d turns to rpm or revolution per minute, the linear velocity of a point, its periphery, will be dn is equal to circumference. Proportion and shapes of gear teeth are well standardized and terms illustrated and defined in figure 20.3 are common all sports gear. The dimension relating to the tooth height are for full depth 14.5 degrees or 20 degrees evolute teeth.
The shape of the tooth. A gear is a cylindrical or ruler-shaped machine component with a teeth that meshes with other cylindrical components to transfer power from one shaft to other. It is primarily used to obtain various torque and speed ratio or to reverse the direction of driving and driven shaft. In generally, gears have an evolved curved tooth profile. There are other types of gear profiles, but they are mainly utilized in specialty applications such as celluloidal gear in clocks and watches. This evolved curve helps the gear transmit power smoothly during rolling action. Every gear has different shape of tooth.
Working drawing of spurgers. A typically working drawing of a spurger is shown in figure 20.9. Since the teeth are cut to the standard shape with special cutters, it is not necessary to show the individual teeth on the drawing. Instead, the addendum and the root circle are drawn as a phantom line and the teeth circle as a center line. Since the machining of the blank and the cutting of the teeth are separate operations in the shop, the necessary dimensions are arranged into two groups. The blank dimensions are shown on the views, and the cutting data are given in a note or table. Before laying out the working drawing, the drafters must calculate the gear dimensions. As in figure 20.9, then the following items should be calculated in order: pitch diameter, addendum, then demdum, outside diameter, root diameter, hole depth, chordal thickness, and the chordal addendum. The dimensions shown in figure 20.9 are the minimum requirements for the spur gears, and the chordal addendum and the chordal thickness are given to the aid in checking the finished gear. Other special data may be given in the table according to the degree of precision required and the method of manufacture.
The design of spur gears normally begins with the selection of pitch diameters to suit the required speed ratio, center distance, and space limitations. The size of the teeth, that is, the diametral pitch, depends on the gear, the speeds, gear materials, horsepower to be transmitted, and the selected tooth form. The complete analysis and design of precision gears is complex. Figure 20.10, as you can see, will quickly yield a suitable diametral pitch for ordinary cut spur gears. The chart is based on the Lewis equation with the Barth velocity modification and assumes gear face width equal to 3 times the circular pitch. For example, determine the diametral pitch and face width for a 5 inches pitch diameter G10400 carbon steel, pinion having 14 and 1/2 full depth, teeth that must transmit 10 HP or horsepower at 200 RPM. Calculate the pitch inline velocity V as follows. V is equal to pi over 12 dPnp is equal to 0.262 times 5 times 200 is equal to 262 fpm.
Worm gears. Worm gears are used to transmit power between non-intersecting shafts that are at right angles to each other. The worm is a screw having a thread of the same shape as a rock tooth. The worm wheel is similar to a helical gear that has been cut to conform to the shape of the worm for more contact. A large speed ratio is obtainable with worm gearing since a single thread worm in one revolution advances the worm wheel only one tooth and a space. Figure 18 double thread worm and worm gear. In Figure 18, a worm and a worm wheel are shown in gauge. The section taken through the center of the worm and perpendicular to the axis of the worm wheel shows that the worm section is identical to a rock and that the wheel section is identical to a spur gear. Consequently, in this plane, the height proportions of thread and gear teeth are the same as for a spur gear of corresponding pitch. Pitch. The actual pitch of the worm is the distance from a point on the thread to the corresponding point on the next thread, measured parallel to the worm axis. The pitch of the worm must exactly equal the circular pitch of the gear. Lead. The lead is the distance that the thread advances actually in one turn. The lead is always a multiple of the pitch. Thus, for a single thread worm, the lead equals the pitch. For a double thread worm, the lead is twice the pitch, and so on. Lead angle. The lead angle is the angle between a tangent to the helix at the pitch diameter and a plane perpendicular to the axis of the worm. The lead angle can be calculated from the formula where dW is equal to pitch diameter of the worm. The speed ratio of worm gears depend only on the number of threads on the worm and the number of teeth on the gear. Therefore, Ng is equal to number of teeth on the gear, and Nw is the number of threads on the worm. For 14.5 standard and volute teeth and single thread or double thread worms, the following proportions are the recommended practice of the AJMA. All formulas are expressed in terms of circular pitch P instead of diametral pitch P. It is easier to machine the worm and the hub used to cut the gear if the circular pitch has an even rational value such as 5/8 inches.
Working drawings of worm gears. Worm gears are used to transmit power between an interesting shaft that are at right angle to each other. The worm is a screw having a thread of the same shape as a rock tooth. The worm wheels is similar to helical gear that's been cut sing a single thread worm in one revolution advances the worm will only one tooth and space. In figure 20.11, a worm and a worm wheel are shown engaged. The section taken through the center of the worm and perpendicular to the axis of the worm wheel shows that the worm section is identical to a rock and that the wheel section is identical to a spur's gear. Consequently, in this plane height, proportion of the thread and gear teeth are the same as far as for gear corresponding pitch.
Bevel gears. A bevel gears is a tooth rotating machine element used to transfer mechanical energy or shaft power between shafts that are intersecting, either perpendicular or at an angle. This results in change in the axis of rotation of the shaft power. Handrails are arguably where bevel gears are most well known. Bevel gears are used to transmit rotational motion and right angle, whereby the two gears' axes intersect.
In Table 20.1, it shows the beaver gear terms, definition, and formulas. Addendum. Addendum is the distance from pitch cone to the top of the tooth measured at the large end of the tooth. Addendum angle. An angle subtended by addendum, same from the gear and the pinion. Back angle is usually equal to the pitch angle. Backing is the distance from base of pitch cone to the rear of hub. Chordal addendum and chordal thickness. For bevel gears, the formula given for the spur gears can be used if D is replaced by D slash cosine F and N is replaced by N cosine F. Crown backing. More practical than backing from shaft use. Dimension C given on drawing instead of Y. Crown height. Distance parallel to the gear axis from the cone apex to the crown of the gear. Dendum. The distance from pitch cone to the bottom of the tooth measured at large end of a tooth. The dendum angle. An angle subtended by the dendum, same for gear and pinion. Face angle. An angle between the top teeth rather, and the gear axis. Face width should not exceed 1/3 A or 10 over P whenever, or rather, whichever is smaller. Mounting distance. A dimension used primarily for expansion and assembly purposes. Outer cone distance. Slant height of the pitch cone, same for gear and pinion. Outside diameter. A diameter of outside or crown circle of the gear. Pitch diameter. A diameter of base of the pitch cone of gear or pinion. Root angle. An angle between the root of the teeth and the gear axis.
Let us now talk about working drawing of bevel gears. As in the case of spur gears, a working drawing of a bevel gear gives only the dimensions of the gear blank. The necessary data for cutting the teeth are given in a note or table. A single sectional view usually will provide all necessary information. Figure 23. If a second view is required, only the gear blank is drawn and the tooth profiles are omitted. Two gears are shown in their operating relationship. On detailed drawings, each gear is usually drawn separately, as in Figure 22, and fully dimensioned. Proper placing of the gear blank dimensions is largely dependent on the manufacturing methods used in producing the gear, but the scheme shown is commonly followed.
CAMS provide a simple means for obtaining unusual and irregular motions that would be difficult to produce otherwise. Figure 20.17a illustrates the basic principle of the cam. A shaft rotating at uniform speed carries an irregularly shaped disc called the cam. A reciprocating member called the follower presses a small roller against the curved surface of the cam. Rotation of the cam thus causes the follower to reciprocate with a definite cyclic motion according to the shape of the cam profile. The roller is held in contact with the cam by gravity or a spring. The problem of the drafter is to construct the cam profile necessary to obtain the desired motion of the follower. An automobile valve cam that operates a flat face follower is shown in Figure 20.17b. Figure 20.17c shows a disc cam with the roller follower attached to a linkage to transmit motion to another part of the device.
Displacement diagram. Since the motion of the follower is of primary importance, its choice of speed and its various positions should be carefully planned in a displacement diagram before the cam profile is constructed. A displacement diagram is essentially a graph which plots the movement of a cam follower against the time. Since the cam's movement is usually constant, then equal time interval can be represented by equal distance along the horizontal axis and the resulting follower movement or displacement along the vertical axis.
Thank you for listening.